Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is just being kind of an introduction to the idea of electromagnetic radiation, or what we call light. So the first thing to realize about light is this. When people were first learning about light, way back in like from Isaac Newton days forward, and people were speculating what it was, the first $1,000,000 question was, was light a wave type of phenomenon or a particle type of phenomenon? That was the first question that people dealt with for a lot. So a lot of experiments were put together to test whether or not electromagnetic radiation had wave properties. Other experiments were to determine if it had particle properties. And the answer to this question is yes. First thing, light, you have to be able to think about it in both wave form and particle form because light has characteristics of both. So I'm going to start by talking about the particle form of light. So the first thing to consider is, what are these particles called? They're called photons. So a photon is, you can think of it as a small particle of light. Now, I'm going to talk more later about the wave characteristics, but some important things about waves. Waves have a frequency and waves have a wavelength. So what a photon is I like to think of it as a little particle that has wave properties. And when you draw a photon, they usually look like this when you draw them in the book, or when you see them in the book. So little particles, like little pictures like this in your book, are representing photons. Usually it's symmetrical. All right, so light does have particle properties. So when you're looking at a flashlight or you're shining a flashlight at something, you can imagine this as basically the light being a stream of particles, basically an infinite number of them coming out of the flashlight. Right? Now, these photons carry an energy with them, and the energy depends on the frequency. And it turns out that the energy of a photon is directly proportional to the frequency. That's an important equation for photons. So we'll say the energy of a photon is equal to some constant, I'm going to write h for now, times the frequency. The constant h is called Planck's constant. Its numerical value is 6.63 times 10 to the minus 34th joule seconds. Right? So that's pretty well enough about the photon part of it. The wave part of it's a bit more complex, a little tougher to describe. So most of this video is going to be about describing the photon properties or the wave properties of light. So big deal. First part is that light has both wave properties and particle properties. The particles are called photons, and the energy of a photon is proportional to the frequency. Now we're going to take a little bit and talk about, well, what creates light, or how is light created? So if you'll give me just a moment here, I'm going to get rid of this. And what I'd like you to imagine here is a conductor. I'm going to kind of draw it now. Give this some dimension here. Again, some conducting material, maybe aluminum or something. Let me give it a little color. And I'm going to put a coordinate system in this. Right here, right at the center of that. Oops. And I'm going to go ahead and draw a really long coordinate system here. All right, so there's my x-axis. Oops. I'll just put a little y-axis here. That's all I need. All right, x, y. And imagine now that a voltage is applied to this conductor. And not just any voltage. I want you to imagine an AC voltage source. I can draw that better than that. All right, so remember, an AC voltage source means this is going to vary sinusoidally. It's going to have a maximum voltage, Vmax sine omega t. And imagine that voltage is applied vertically like this. Now, that means that if the voltage is going to do this, basically. And you'll notice that what that means is half the time the charge is going to be driven up. So if I were to actually put like pluses and minuses in this, and I'm going to not switch colors on the charge for now, that when the voltage maybe is in this polarity, that's going to give us a plus minus like so. And when the voltage is in the other polarity here, this picture is going to look like this. So it's very important to realize that the charge configuration on this beam is going to vary back and forth between plus minus and plus minus. Now, I'm going to talk about this one right here, this configuration, plus minus. And I'm going to pick a spot and space out here, maybe like right here. The electric field vector, due to this positive charge, points down and right. And if you'll humor me, I'm going to go back actually and change the color on that to I don't know, blue. So there's the electric field vector due to this positive charge. Now, this negative charge is going to create an electric field vector towards it. A little review here if you're getting ready for my final exam in physics 2. Electric field direction is defined as the force direction on a small positive test charge. So remember that the electric field points away from positive charges but towards negative charges. Right? So that's where I'm getting these field directions. The field due to this positive charge, down and right. Field due to the negative charge, down and left. Now, notice that the net field, all right, by the symmetry of the problem here, is going to be down. And it's equal to the vector sum of the two. All right, so this is the electric field due to this guy. This is the electric field due to this guy. This is the important one right here, that the net electric field points down. Now, when we switch the charge configuration now to plus, scribble that out, minus, the electric field vector reverses direction. I'm not going to draw all four now. I'm just going to draw this one. This electric field vector is going to just reverse direction. Whoops. Not what I wanted there. Blue. There we go. Whoops. One more try. There we go. Now, when we go back to the other configuration, again, the electric field is down. When we go back to this configuration, the electric field is up. So it's important to realize that anywhere on axis here, the electric field vector is either up or down. Now let's say I pick a point out here, like this point right here. And let's just say hypothetically that at some point in time, the electric field vector points down. Imagine for a moment that this can instantaneously change direction. So with this electric field vector, the assumption there to have that electric field vector down was plus minus. Imagine that I can instantaneously change that to plus minus. And again, imagine it truly instantaneously. Well, if that instantaneously changed, it just, for lack of a better way to describe this, it takes a little time for that effect to propagate over to the right. So there's going to be some sort of time delay before this electric field changes direction. Then it'll change. Boom. And that effect is radiation. So if you think about what radiation is, it's a changing electric field propagating through space. So what you can imagine here now, imagine this buzzing back and forth, plus minus, plus minus, plus minus. The electric field vectors can be described by a waveform. All right, so the electric field vectors might look something like this in this picture. Now imagine that this entire wave is moving to the right. And if I pick a point here, whoops, as these electric field vectors go by, like at a certain time the electric field would have this magnitude and then be a little less and then a little less, and here the electric field would be 0. Again, you got to imagine at this point. When this point in the curve gets here, the electric field vector is down. When this point in the curve gets here, the electric field vector is down and it's a maximum, and so forth. So you have to imagine this waveform of electric fields moving to the right with some sort of speed, v. Now that speed is called the speed of light. All electromagnetic radiation travels at the same rate. 3 times 10 to the 8th meter per second. That's called the speed of light. It's usually written with the letter C in most books, and it's one of these fundamental constants. So, from a wave standpoint, to ask, well, what is radiation? It's an electromagnetic wave traveling through space. It's a disturbance in the electric fields. Now you notice that I use the term magnetic, but there's nothing. We don't see anything about magnetism here. Well, I'm going to try to describe this in short order, as kind of quick and simple as I can. In order for this charge configuration to change from plus minus to plus minus, you have to have a current. Imagine for a moment that the current is down. Now, it's important to realize, remember, the voltage, if the voltage is a sinusoidally varying voltage source, this current is going to be oscillating back and forth. But just imagine for a moment the current is down. That means we're going to have magnetic fields around this, and those magnetic fields are circular around this, and they would be in this direction. So hopefully you've watched my videos on magnetic fields around wires. You mentally grab the wire, thumb in the direction of the current, your fingers roll in the direction of the magnetic field lines. So out here in the plane, it's important to realize the magnetic fields are this way. And it's kind of hard to describe what I mean by that. Let me draw them in here, and then I'll talk more. Let me draw some of these. This is a picture I'm not very good at drawing. If you've got your textbook, I'm sure there's a better one. All right, and let me give some directions to this. So imagine a coordinate system like X, Y, Z, with Z coming right at you. These electric field vectors are in the XY plane. They're vertical. These magnetic field vectors are in the XZ plane. They're horizontal in this picture. So this is what we call an electromagnetic wave. So as far as what is electromagnetic radiation? It's a wave, and in general, a wave is a disturbance. So for example, a sound wave is a disturbance propagating through the air. A water wave is a disturbance in the surface of the water. Well, an electromagnetic wave is a disturbance in the electric and magnetic fields in a region in space that propagates at 3 times 10 to the 8th meter per second. So, this is my best description here as to how things radiate. Now, if you think about like what's causing this, all right? Well, in this example, it's this charge oscillating back and forth. So basically, any time you move charge around like this, you're going to create this disturbance in space. So I like to say, the simplest way I can put this, what causes electromagnetic radiation? Wiggling charge. Anytime you have wiggling charge or charge moving or accelerating like this, you're going to be radiating. And that's why all matter radiates. Everyone listening to this video, you are currently radiating right now. You're radiating electromagnetic waves in the infrared spectrum. I'm going to talk about that in my next video. And that's because when we get down to the scale of the atom, an atom has a nucleus positively charged. Typically, it's got electrons going around it. I'm going to consider just basically maybe a hydrogen atom here, so it would have maybe one electron going round and round. This is by far not to scale, but this electron going round and round is very similar to this charge going up and down, up and down. And the nucleus itself typically is kind of vibrating back and forth. So all atoms just naturally radiate energy. Even ice cubes in your ice freezer are radiating. They're just radiating at very, very low energies. So I'm going to save that for my next video. Important things about this video. What is electromagnetic radiation? Well, it's a wave, and it's a particle. Particles are called photons, and these photons carry an energy proportional to the frequency. Also, you can think of EM radiation as an electromagnetic wave. It's a disturbance in the electric and magnetic fields propagating through space at 3 times 10 to the 8th meter per second. An important equation for electromagnetic radiation is this. For a wave phenomenon, waves have a frequency and they have a wavelength. Wavelength is usually denoted with the Greek letter lambda. In this picture, one wavelength would be the distance between any 2 points on the wave. So like maybe from here to here, that would be one wavelength. And how these variables are related is very, very important. So in general, for any wave phenomenon, velocity is equal to frequency times wavelength. And what this allows us to do, since all wave-like phenomenon, or all electromagnetic waves, travel at c, the speed of light, we can rewrite this equation. C equals F times lambda, the wavelength. And now basically, if you tell me a frequency, I can tell you a wavelength, a lambda. Or if you give me a lambda, I can tell you a frequency. So this equation allows us to go back and forth between frequency and wavelength. A very important fundamental here of this equation, if you look at an equation like, let's say 12 is equal to x times y, and you think about the different values that solve this. X could be 1, y would then be 12, or maybe 2, 6, or maybe 4, 3, or maybe 12, 1. Notice that when x is small, y is big. When x is big, y is small. This equation has that same property. When you have very high frequency, that means you have very low wavelength. And when you have low frequency, you have long wavelength. So I think I'll save that for my next video. Hope everybody watching this has at least a little idea of what electromagnetic radiation is. Sorry about the kind of messy picture, but have a great day.